Now let us talk about the estimation of frequency and rate of change of frequency. Now if the frequency deviation from the nominal value and the rate of change of frequency at time t is equal to 0 is delta omega and omega dash, then the frequency at any time t can be given as omega t is equal to omega naught, that is fundamental frequency, plus delta omega, the change in frequency, and omega dash t, that is rate of change of frequency component. Now if you integrate this expression, you will get the phase angle, and this can be represented as phi t equal to phi naught plus delta omega t plus half omega dash t square. Now if you compare this expression with the quadratic equation, say phi t is equal to a naught plus a1t plus a2t square, we can say a naught is equal to phi naught, a1 equal to delta omega, twice of a2 equal to omega dash. Now in terms of frequency and rate of change of frequency, we can simply write a1 by 2 pi equal to delta f and a2 by pi is equal to f dash. Now if you are taking sample from the field and the sampling time is delta t, which is being processed by the PMU, the above equation, if you put the sample values in this above equation, we can collect this data in the matrix form. How we can write? We can write column vector as phi naught, phi 1 and so on, and the matrix which corresponds to the sample data which we are receiving for the field, we can simply write as 1 0 0 1 delta t square and so on, and the unknown column vector, that is a0, a1 and a2. So this information we are getting from the PMU, that is the phase angle estimation. From the PMU we can get the value of phase angles, and then the values for unknown a0, a1, a2 can be calculated. Now in this, if we keep the sampling rate constant, this matrix will remain constant. So what we can write? We can write in matrix form this phi is equal to BA. B will be the coefficient matrix and can be stored as pre-calculated because it will remain constant for constant sampling frequency. Now unknown is a vector. So what we can do? We can utilize weighted least squares approach, which we commonly use in state estimation. So what we use there, the same can be utilized here, that is weighted least square approach, to find out the value of unknown A. So A can be written as B transpose B whole inverse B transpose phi. So by using this expression, we can find out the value of vector A. Since B is a constant quantity, B transpose B inverse B transpose can be pre-calculated and stored somewhere for a constant sampling frequency, and immediately after getting the value of phi, the value of A can be calculated. Now after you get the value of A, you can simply calculate the value of delta f and f dash, because delta f is a1 upon 2 pi and f dash is a2 by pi. So in this way you can find out the value of frequency change and rate of change of frequency. How you will calculate the error in frequency measurement? Frequency error is given by mod of true value of frequency minus measured value of frequency, or we can write delta f true minus delta f measured mod of that quantity. To calculate the error in rate of change of frequency, we can calculate the value of error in rho of as mod of df by dt true minus df by dt measured. Now let's talk about the PMU compliance requirement. As per IEEE C 37.118-2005, the PMU steady state compliance is given as follows. First, we talk about the total vector error. Total vector error, that is TV, is defined as the real value of the phasor computed minus real value of the true phasor whole of square plus imaginary value of phasor calculated minus imaginary value of the true phasor whole of square divided by the square of real and imaginary components of the true value of phasor. So we can calculate the total vector error, and total vector error has the maximum value, that is maximum permissible value is 1% as per IEEE C 37.118-2005 standard. Now the permissible synchronizing error in PMU is 1 microsecond. That is how the PMU clock is synchronized with 1 PPS signal. The maximum delay is possible equal to 1 microsecond. So if you translate that into an angle value, this will come out to be 360 degree into 50 into 10 to the power minus 6 equal to 0.018 degree. So that is for 50 hertz. So if you just replace 50 by 60, you will get the maximum synchronizing error for 60 hertz system. That will come out to be 0.022 degree. Now if the total vector error is solely because of phase angle, the maximum error possible will be 0.57 degree. Now if you translate it into the time, so correspondingly the maximum error will be of 26 microsecond for 60 Hz system and 32 microsecond for 50 Hz system. Now, steady state compliance requirements for P class and M class of PMUs are different, which we will see in the next few slides. The P class of PMU does not have anti-aliasing filter. Now, the compliance verification, how we do the compliance verification for the phasor measurement unit. A calibration device is utilized to verify the performance of PMU in accordance with the C 37.118-2005 standard. The document shall be provided by any vendor who is claiming the compliance with this standard will include performance class of the PMU, measurements that meet the class of the performance, test results demonstrating the performance, equipment settings that were used in the testing, environmental conditions which were used in the testing, and error analysis if the verification system is based on an error analysis. Now, PMU verified for a particular performance class shall meet all the performance requirements specified for that class at all required reporting rates. So what are the various boundary conditions for which the vendor has to seek the compliance? Let's see that. The test condition for that is that all compliance test has to be performed with all parameters set to standard reference conditions. The reference conditions for all tests are given as voltage at nominal, current at nominal, frequency at nominal, voltage, current, phase and frequencies are constant. Signal total harmonic distortion, that is TSD, should be less than 0.2% of the fundamental. All interfacing signals should have less than 0.2% of the fundamental. Measurements at the reporting rate lower than 10 frames per second shall not be subject to dynamic performance requirement. So for dynamic performance requirement, the frame rate should be more than 10 frames per second. All testing to certify compliance shall be performed at standard laboratory test conditions, which will include temperature, which should be 23 degrees centigrade plus minus 3 degree, and humidity should be less than 90%. Now, as per the C37.118-2011, the standard is divided into two parts. IEEE C37.118.1, which addresses the dynamic performance requirements such as frequency and rate of change of frequency, and IEEE C37.118.2 addresses the issues related to synchrophasor data communication. Now let's first talk about the steady state synchrophasor requirements. So if the signal frequency is at nominal, that is fundamental frequency, and if it is changing between plus minus 2 Hz, still the total vector error for P class should be 1 and for M class should also be 1. If there is a voltage change from 80% to 120%, still maximum TV, that is total vector error, should be 1 in both of the cases. While in case of M class, the voltage magnitude can change from 10% to 120% of rated value. For current, the value can change from 10% to 200% of rated, and still TV should be 1. If the phase angle is changing slowly within the range of plus minus pi radians, still the TV requirement is 1. Now, steady state synchrophasor measurement requirement for harmonic distortion. If the reference condition is that TSD should be less than 0.2%, and now if there is 1% each of harmonic up to 50th of harmonic, still the TV should be 1, and same is for M class. Now, out of band interference, it is not defined for P class, but for M class, the maximum TVE can be 1.3%. Now for frequency and rate of change of frequency measurements, if the frequency changes between plus minus 2 Hz, the maximum frequency error possible is 0.005 Hz for P class, and rate of change of frequency maximum possible is 0.01 Hz per second for P class. Similarly, for M class, these values are 0.005 Hz and 0.01 Hz per second. For harmonic distortion case, if TSD is less than 0.2%, in that case, the frequency error is 0.005 Hz for frame reporting rate more than 20, and for frame reporting rate less than 20, still it is 0.005 Hz. For both of the cases, the maximum rate of change of frequency error is 0.01 Hz per second. In case of M class, these values are 0.025 Hz if the frame rate is more than 20, and 6 Hz per second as maximum rate of change of frequency error. For frame rate less than 20, the value of maximum frequency error is 0.005 Hz and 2 Hz per second as rate of change of frequency. In case of out of band interference, for P class it is not defined. For M class, maximum frequency error possible is 0.01 Hz and maximum rate of change of frequency error is 0.1 Hz per second. Now let's talk about the dynamic compliance. So we do generally frequency and amplitude modulation test, ramp test, and the step change test for checking the dynamic compliance of phasor measurement unit. For frequency and amplitude modulation test, we check if the PMU is designed to reflect the small signal, that is low frequency oscillations, or not. The modulation frequency shall be varied in steps of 0.2 Hz or smaller over a specified range. The TV frequency error and rate of change of frequency error shall be measured for compliance at the given reporting rate. Now suppose the modulation level is, say, the amplitude is modulated with 10% and angle is modulated with 10% with respect to the reference condition, then in that case the total vector error can be 3% for P class and same is for M class. Now if we are not doing the amplitude modulation but we are having the angle modulations, in that case also the total vector error should be equal to 3% in both P and M class. Now let's talk about the frequency error and rate of change of frequency error. If frame reporting rate is more than 20, the frequency error for P class is 0.06 Hz. Maximum rate of change of frequency error is 3 Hz per second. For M class, the values are 0.3 Hz and 30 Hz per second. If the frame reporting rate is less than 20, then frequency error is 0.01 Hz. Maximum rate of change of frequency error is 0.2 Hz per second for P class. For M class, the same values are 0.06 Hz and 2 Hz per second. Now let's talk about the frequency ramp test. The measurement performance during system frequency change shall be tested with linear ramp of the system frequency applied. So what we will do in this case, we will have the linear ramp with 1 Hz per second, that is we can ramp up and ramp down. In both of the cases, for P class the ramp range is plus minus 2 Hz and for M class the ramp range is lesser of plus minus frame reporting rate by 5 or plus minus 5 Hz, and in both of the cases total vector error should be 1%. Now when we compare the frequency error and the rate of change of frequency error, for M class it is 0.005 Hz and 0.1 Hz per second. Now the third one is the step change in magnitude and phase angle test, where we check the delay time and overshoot. So if the magnitude is changing with plus minus 10%, keeping the angle value same, in that case the response time of the signal should be 1.7 by f naught. Delay time should be 1 by 4 times the frame reporting rate, and maximum overshoot should be 5% of the step magnitude. For the M class, the details are given below, and the delay time will be 1 by 4 into frame reporting rate, and the maximum overshoot possible is 10%. Now if we are doing change in the angle, that is angle step change is there, keeping the amplitude same, still the requirement for the response time, delay time and maximum peak overshoot will remain same. Now let's talk about the frequency and rate of change of frequency. For P class, for magnitude test it will be for 3.5 by f naught, and rate of change of frequency will be 4 by f naught, and for the phase angle test the value will remain same. In case of M class, there are lot of conditions with respect to reporting rate. So with the change in frame reporting rate, the value of frequency error and rate of change of frequency error will change. Now the PMU compliance requirement for the latency. The latency in measurement reporting is critical factor for measurements used in real-time applications, particularly in controls. So in addition to measurement latency, there are many factors which contribute to the reporting delays, such as communication coding and the transmission distance. The application using the data shall take into account all the delays, including the measurement as well as the communication and the transmission delays to determine the system performance. So for P class, the maximum delay possible is 2 by Fs, that is the frame reporting rate, and for M class it is 5 by Fs, that is 5 by the frame reporting rate.